So in my previous session, I had made a revision exercise on arithmetic progression and geometric progression. We'll do a similar one today, but this time we'll be concentrating on permutation and combination. As far as I remember, I didn't do any sum as such from permutation and combination, so we'll be doing sum in this session. So the first cell says, prove that the product of any r consecutive natural numbers is always divisible by r factorial. So the first trick of this sum is you can take the r consecutive natural numbers as 1, 2, 3, 4, 5, 6, 7 up to r, which won't exactly serve our purpose. But the next obvious term that you can take it is n plus 1, n plus 2, n plus 3 up to n plus r minus 1. In fact, that itself also won't serve our purpose in this sum. So for this sum, that's something that probably you'll learn with experience from solving sums, or your intuition needs to work hard. So what the r consecutive natural numbers that we'll be considering here are n plus 1, n plus 2, n plus 3 up to n plus r. So this is the first, this is the second, this is the third. This is the rth consecutive natural number that we have used under consideration. And we need to divide it by r factorial, and we need to say that these are consecutive natural numbers, their product is divisible by r factorial. So one of the ways to do it is we divide the product of these r consecutive natural numbers by r factorial and find out the result. If it is divisible, then this expression, the product divided by r factorial, this should come out to be a proper integer. It needs to be a positive integer, 2, 3, 4, 746, anything, but it needs to be a proper positive integer, not some point form like 7.23 or 6.41. So that is what we will do. We have expressed it as n plus 1, n plus 2, n plus 3 up to n plus r by r factorial. In the next step, what I've done is I have multiplied 1, 2, 3, 4 up to n on both the numerator and the denominator. So I've multiplied n factorial. I've multiplied because this part is actually n factorial. So I have multiplied n factorial in the numerator and the denominator of the expression. Now what you see is when I multiply 1, 2, 3, 4 up to n, and then I keep on multiplying n plus 1, n plus 2, n plus 3 up to n plus r, I have essentially this n is essentially the preceding term of n plus 1. So I have continued this multiplication till n plus r. So this n factorial combined with the initial numerator gets transformed into n plus r factorial. And I simply use this denominator as n factorial, and I have r factorial. So I have n plus r factorial by n factorial r factorial. Now, if you remember the expressions for combination, when we had NCR, the expression for, or the expansion for NCR was n factorial by r factorial into n minus r factorial. If you replace n with n plus r, you get n plus r CR, which is n plus r minus r factorial by n factorial into n plus r minus r factorial. So that essentially gets reduced to n plus r factorial by n factorial r factorial. So if if this is the expansion, let's say that I reduce it and I put it in a notation form, I get it as n plus r CR. Now, which is obviously a positive integer, needless to say. So when I divide these r consecutive natural numbers by r factorial, and if I solve it, I get a positive integer. So that naturally says that this product of r consecutive natural numbers is divisible by r. So that's the first sum done. Next sum is an interesting one. How many different factors can 2160 have? So the first step that I have done is I have expressed 2160 as in product form using the prime numbers. So it's you can use it, you can use a calculator or you can do mental arithmetic. And the expression is 2 to the power 4 into 3 cube into 5. So I again expressed it in multiplication form. You don't need to do it. Now the trick here is we need to find different factors for 2160. So I need to choose combinations of these few numbers that I have in different forms. The trick here is there are four, yeah, there are four numbers which are 2, so they are identical. There are again 3 numbers which are 3, so they are again identical, and we have a third term which is of a different kind. So we essentially have 3 types of items that we can choose from. So we have to choose from 3 prime numbers, where 4 are of one kind, they are 2, 3 are of a second kind, they are 3, and 1 are of a third kind, and we have 5. So if you remember, we had one of those restricted combinations that we had discussed. I'll link it up. There we had discussed in details how we find out the expression for this. I'll be using that exact procedure. And since we have 4 repetitions, 3 repetitions, and 1, we can put it in 2 forms. The first one is, it's I think in my example, I had used P are of one kind, Q are of some second kind, and R are of some third kind. So it was P plus 1 into Q plus 1 into R plus 1 minus 1, because this is to adjust with the fact that we need to choose at least one combination. So that gives me 4 plus 1 into 3 plus 1 into 1 plus 1, because the repetitions are 4, 3, and 1. So I get 39. Another way is, there was the second restricted combination that I discussed, where there are few m more which are not identical in nature. They are all different types. So 5 actually is 1 which is of a different kind. So again, we can, in that case, it was 2 to the power m into p plus 1 into q plus 1 and so on. So going by that logic, I have 2 to the power 1, because there's just one other article which is of different kind. So I get 2 to the power 1, because I've replaced m equal to 1. So 2 to the power 1 into 4 plus 1 into 3 plus 1, again minus 1 for the same logic, and that again gives me 39. I've essentially used this 1 plus 1 and I have replaced it by 2. So these are the 2 procedures in which I can tackle this sum. It's a very interesting sum, to be honest. And that is how we find the different factors of 2160. The next sum is another of my favorite types. So how many diagonals does an n-sided regular polygon have? Now, a diagonal is defined by joining any 2 points or any 2 vertices of a polygon, other than, like, if you join 2 vertices of a polygon which are one after the other or one beside the other, you will essentially get a side of the regular polygon. So those are not considered. So that is the concept that I'll be using here. So let's say that I have an n-sided regular polygon. So there are n points that I have under consideration. So if I have a pentagon, there are 5 vertices to consider. So number of ways in which any 2 points from these n vertices can be joined is nc2, the most obvious explanation. Of these, if I join any 2 sides which are one beside the other, so this or this or this, these are essentially the sides. So they are not the diagonals of the n-sided regular polygon. And you see there are essentially 1, 2, 3, 4, 5. So since we have considered a pentagon, we have 5 sides, and obviously in an n-sided regular polygon we will have n sides. So of these nc2 ways in which we have joined any 2 points from the n-sided polygon, of these, n are the sides of the regular polygon, because we have considered number of ways in any 2 points can be joined. So we have considered the sides of the polygon as well. So we need to deduct that, and what we get is nc2 minus n. So if we take an example of a regular polygon, so we have 5c2 ways in which we can join any of these points, any of these 2 points in different ways. So we have 5c2 ways in which we can join these points, of which 1, 2, 3, 4, 5. 5 of them are the sides of the polygon. So those are not the diagonals. So we essentially are left with 5c2 minus 5 ways in which we have the diagonals covered. So we do not consider this, but we do consider this. We consider this. These are the diagonals of the pentagon, but the sides are not considered. So we have 5 nc2 minus n. This is this very specific reason why I considered an n-sided regular polygon and not a five-sided regular polygon, because you can essentially use this as a formula as well. So whatever sided polygon you're given, the answer will always be nc2 minus n. So for a hexagon, it will be 6c2 minus 6. For a decagon, it will be 10c2 minus 10, and so on. So the final sum again, this was a comparatively shorter session. So the next sum is, in how many ways can our items form a ring? This ring is a very typical sum that is used to confuse students, in fact. So we need to arrange items in a ring and not in a line. So the trick here is, since it's a ring, you can put 1, 2, 3, 4, 5 in this order, or again you can put it as 1, 2, 3, 4, 5. But what should I say? The arrangement itself is not exactly different. I'm putting 1, 2, 3, 4, 5 one beside the other, so they are not changing. But I have changed the relative positions of these. No, I should say I have changed the position of the items, but the relative positions have not changed. So in this case, when I consider a ring, or I consider a ring format in which the items have been arranged, I need to consider the relative position and not the absolute positions, because the absolute positions can change, but the essential arrangement can remain the same. So here we need to find the relative position of the items. Now, in order to find the relative position, I need to fix any one item. So if I fix one item here, then I can change these positions among themselves, and it won't matter uh, to the arrangement of the items in the ring form. So what I do is I fix this item here, and if I have they have told me R items. So if I have R items to be arranged in a ring and I fix one item, I essentially have R minus 1 items to be rearranged. And as you know, R minus 1 items can be rearranged among themselves in R minus 1 factorial ways. So that is essentially the answer of the sum. So in how many ways can R items be formed, items be arranged in a ring? That the answer will be R minus 1 factorial. Again, by like the previous sum, I have used a general form such that if you get a specific value of R, you can always use this as a formula. So if you are asked to find the way in which 10 items can be formed in a ring, the question's answer will be 9 factorial. And if you are asked to find the ways in which, let's say, 500 items can form a ring, the answer will be 499 factorial. So that is the summary of the exercise. And usually sums like this are very important in the chapter of computation and combination.